In general, then, our differential equation can be expressed as the column vector y prime equals p times a column vector y plus a column vector g. And if g is non-zero, this equation is non-homogeneous. If g happens to be 0, then the equation is homogeneous. Now, we've already seen a homogeneous equation, the original equation we started discussion of the chapter with, where I believe we had y1 prime equals 5y1 plus 2y2, and y2 prime equals 4y1 plus 3y2, if I recall correctly. Our P matrix was just the matrix 5, 2, and 4, and 3. Now, if y1 and y2 are solutions of a homogeneous equation, then it follows that y1 prime equals py1, assuming they're solutions of this homogeneous equation, that y1 prime equals py1 and y2 prime equals py2. And from that it follows that y1 plus y2 prime equals p times y1 plus y2. And the reason for that is very simple. The differentiation is linear, so that this is going to just be y1 prime plus y2 prime, and matrix multiplication is linear, so this is just going to be py1 plus py2. And if we have y1 prime equals py1, y2 prime equals py2, it follows that y1 prime plus y2 prime will equal py1 prime plus py1 plus py2. And whether you understood that, it's just a matter of writing it out. The linearity of differentiation and of matrix multiplication extends to constant multiples of functions and sums of constant multiples of functions, so that if y1 and y2 are solutions, just writing out a very similar argument tells us that c1y1 plus cy2y2 is a solution. And in our previous example, which I've alluded to down here if I don't knock everything across the room, a solution I alluded to down here, remember we had solution c1 e to the t times 1 negative 2 and c2 e to the 7t times 1 1. Or just e to the t times 1 negative 2 and e to the 7t times 1 1. Any linear combination, c1 times this plus c2 times this, still gave us a solution to our original equation, and gave us in fact the general solution to our original equation. A fundamental set for a system of equations is going to be very similar to a fundamental set for a system of linear equations for functions of a single variable. The definition is just going to be pretty much the same as the previous definition. The only difference is that these are now vector functions with many components, but a fundamental set would be a set of solutions with the property that every solution can be expressed as a linear combination of vectors in that set. And again, coming back again to our first problem, the fundamental set for that problem was e to the t times the vector 1 negative 2, e to the 7t times the vector 1 1. Our general solution was this, and this multiplied out to this, telling us that our general solution y of t could also have been written as y1 y2 with y1 equals c1 e to the t plus c2 e to the 7t, y2 equal negative c1 e to the t plus c2 e to the 7t. This has all been written out before, just reminding you.